Hello, ladies and gentlemen. My name is Margreth Tadie. I'm presenting work conducted by one of my master's students, Mr. Kieran Kenpass, who is the first author. The title of my talk today is Using Life Cycle Assessment as a Design Tool to Recover Value from Gold Mine Tailings, and this is a Witwatersrand case study. What we aim to do is to use life cycle as a semi-quantitative tool to develop flow sheets for reprocessing of gold mine tailings. And this is an activity which is taking place quite extensively in South Africa. So the Witwatersrand ore body is reported to be one of the world's largest gold reserves, but the declining grades are making mining expensive and increasingly unprofitable. Hence, the gold mining sector in South Africa has reduced significantly. On the other hand, some mining operations in the region are managing to prolong their operations via reprocessing of old tailings storage facilities, particularly as grades decline towards those of tailings, as seen here in this graph. Now, other companies are in the business of only processing tailings and doing it profitably. Legislation is also driving reprocessing for environmental reasons. Some of the old tailings storage facilities were previously unlined, and others have been compromised by migration of communities to settle within these regions. So a case is being put forward for reprocessing tailings as an environmental strategy for mitigating negative impacts. Now, in poorly managed tailings, these impacts include dust pollution, acid rock drainage generation, heavy metal contamination, poor land use, and so forth. So advantages in reprocessing are therefore available. The opportunity for improvement of long-term sustainability of tailings exists, and this is due to reconstruction of tailings storage facilities using modern technologies, e.g. the lining of tails, backfilling, and other technologies. And reclamation of land is also possible, as material can be relocated from multiple TSFs to a single, more stable TSF. But the clear problem with reprocessing, however, is that it is an exercise that is associated with costs. It requires infrastructure that might involve a capital input. And that being the case, there may be little motivation to take the opportunity to ensure the process is designed to maximize both profit and reduce environmental impact. So in this work, we wanted to investigate reprocessing of tailings to achieve both value recovery of gold and evaluate the opportunities for reducing the ecological impact of tailings. So we developed flow sheets based on existing lixiviant technologies, cyanide and thiosulfate. And comparisons of these flow sheets was expected to give an indication of the potential impacts of green chemistry alternatives. In these flow sheets, we deliberately incorporated processes, as far as these processes exist, that is, to reduce the release of harmful contaminants and effluent. And then life cycle assessment was used to evaluate the impacts of each flow sheet. It was also used to evaluate contributions of individual sections of the flow sheet on environmental impact. Ultimately, the balance between recovery of gold and environmental impacts of these processes is used to qualitatively inform choice in process design. So a case study of the Witwatersrand, as previously mentioned, was made, and each flow sheet was modeled to produce the same amount of gold. This is the flow diagram that shows the methodology that was followed in the work. The case study was identified through a mineralogical survey of tailings dams in the Witwatersrand, and this was done in the open literature. So selection of the case study was based on availability of mineralogical and geochemical data, and this was necessary for effective modeling of the flow sheets. Unfortunately, not a lot of this information is openly available. So mineralogy informs the processing strategy. The mineralogical data was evaluated to identify baseline processes in literature and current state of the art. This was for flowsheet development. Then mass and energy balances were conducted for the proposed baseline flowsheet using HSC9 software. Subsequently, GABI LCA software was used to quantify the environmental impacts of the technologies incorporated and the entire flowsheet. Following that, an alternative flow sheet was then developed, and it was based on a different technology, of which after assessing different existing technologies, thiosulfate was selected because the technology is currently operational. So we also wanted to identify opportunities to further reduce environmental impacts. The simulation and LCA results of both flow sheets were then compared against one another, as well as environmental regulations, and in order to identify flow sheet and technologies that minimize the burden to the environment. Opportunities to further reduce environmental impacts of the process flow sheets were also identified through a sensitivity analysis. So this is the first flow sheet that was developed, and it was based on cyanidation. Cyanide is to date the most effective and economic lixiviant used to recover gold. The first flow sheet was developed based on the Ergo Tailings Reclamation Plant. It's described in Bosch 1987, Marsden and House 2006, and Fleming et al. 2010. And some of the processing approaches are currently being used to treat tailings at the moment in South Africa. So key sections in the flow sheet include froth flotation to concentrate gold-bearing sulfide material, cyanidation of gold as the key extraction method, zinc cementation for recovery of gold, and the particular choice here was informed by challenges in copper and gold separation at low concentrations during cyanidation. Then smelting to recover gold bullion. Now, ecological considerations incorporated in the flow sheet include uranium extraction, and uranium has long been known to occur in significant amounts in the Witwatersrand. Cyanide destruction, SO2 scrubbing after roasting, and arsenic removal. So for the LCA, the system boundaries for the cyanide and thiosulfate processes are shown by the green line and the blue line for foreground, which is processes involved in generating the functional unit, i.e. gold, and background processes, which is manufacture of raw materials used in the process as well as energy resources. A cradle-to-gate evaluation was conducted to allow the background processes to be accounted for, and the functional unit was a kg of gold. The life cycle inventory, which is the data used in the impact assessment, was compiled from material and energy resources, products, and emissions, which were obtained from modeling the flow sheets. Then finally, life cycle impact assessment was performed, and this involves the classification of the LCI data to an impact category and then translating this data to environmental impact categories. So the recipe method, which is reported in literature, was used, and this method is also commonly used for mining LCAs. Then onto this thiosulfate flow sheet. This flow sheet was adapted from the Barrick Gold Strike run-of-mine process, and that's described in Choi 2016. Now, key processes include, again, froth flotation to concentrate gold-bearing sulfide material. Extraction of gold is through thiosulfate leaching. Elution of gold from resin, followed by electrowinning of the electrolyte and then smelting to produce gold. Ecological considerations incorporated in the process included uranium extraction, thiosulfate regeneration and lixiviant recycle, resin regeneration, trithionate manufacture, which is regeneration of the eluent, and this is for stripping gold from resin, arsenic removal from solids, and gypsum precipitation. Additional calcium is introduced in this particular flow sheet in the form of calcium thiosulfate. And the same approach as described before was taken for the LCA. Now, only some select results will be shown. This is just to provide a picture of the type of information gained from the exercise. After modeling the two flow sheets, the concentration of some heavy metals and their comparison to environmental regulations for soil are shown in this table. The regulation is used as a measure to show how benign the material is, and this is the most stringent regulation. It doesn't actually apply to industrial effluent. So both flow sheets showed reduction in the heavy metal content, and where increases are observed, these metals were introduced through processing. For example, lead is introduced into the zinc cementation process as lead nitrate, and manganese is introduced in both flow sheets as manganese dioxide, and that's for uranium leaching. Both these processes are necessary to obtain a high purity product from the plant, so a balance needs to be reached. I haven't shown effluent water emissions and air emissions, but these can be deduced from life cycle assessment data, which is to follow. But before I move on to the life cycle assessment data results, let me just describe the impact categories that we looked at. We looked at 19 impact categories, and these categories cover broadly human health, ecotoxicity, air pollution, and ionization radiation. So over to the LCA results. Overall, not shown in this figure, the LCA showed that the thiosulfate flow sheet had lower impacts than the cyanide flow sheet. Now in this figure, we have a hotspot analysis for the 4 background processes. These are the resource inputs into the process. And from these, we get the following highlights. Electricity supply to the cyanide flow sheet had the greatest impact on the ecosphere, i.e. all 19 categories, impacting 12 of 19. The differences with the thiosulfate is in agitation requirements. It was greater in this flow sheet because of the implementation of cyanide destruction. Secondly, wastewater treatment or effluent sent to wastewater treatment, which was incorporated into the flow sheet, had significant impact, and it affected 7 of 19 impact categories. Now, the wastewater treatment data set produces an activated sludge that contains nitrogen, phosphorus, and potassium. So despite their negative impact, these can be potentially valorized. As a positive, the impact on freshwater consumption created by water treatment was negative, i.e. it was reduced. The hotspot analysis on the thiosulfate background processes showed the same resources, i.e. electricity and wastewater treatment, had the greatest impact. The same number, 12 out of 19 impacts, were greatly affected by electricity consumption. And it should be noted that electricity consumption in this flow sheet was 3.7 times lower than in the cyanide flow sheet. Wastewater treatment had notable impacts, i.e. above 10%, on 4 out of 19 of the impact categories. And this is because of recycle of water. Freshwater consumption, again, was positively affected. Now, the results in water treatment are very dependent on the data sets used, so we treat these negative impacts with caution. Finally, in the foreground processes, they also indicate that thiosulfate as a lixiviant has less impact on the ecosphere than the use of cyanide. And this is a function of the manufacture of cyanide. So from the background processes to the foreground processes, this table gives a ranking of subsections, i.e. different technologies within the flow sheet. Now, the LCA methodology evaluates environmental impact of elementary inputs and outputs, and it doesn't allow analysis of unit processes and chemical species. So to overcome this, we used a methodology by Pennington 2004 to obtain quantitative impacts of specific chemical species emitted to the ecosphere. The chemical species were then traced back to the unit processes producing them, giving these results. So here I show the impacts of different technologies in the form of endpoint impact categories, specifically human health, ecosystem quality, and resource efficiency. The top 5 processes contributing to each of these categories are dominated by cyanide-related processes in the flow sheet, such as lixiviant management, wastewater treatment, and extraction of gold. Uranium leaching and recovery show up as having significant impact, and that's due to the chemicals used to remove the uranium. Again, a trade-off. Other processes related to increasing recovery of gold, such as flotation, roasting of sulfides, appear lower down in the ranking, and these will become more relevant on impact if the lixiviant in the flow sheet becomes more ecological. Lastly, a sensitivity analysis was conducted, and it was conducted on the background processes because they had more significant impacts on the ecosphere. Therefore, the sensitivity analysis was conducted on electricity, lixiviant, and water treatment. So here we see the impact of a 10% increase in electricity utilization, lixiviant use, and effluent sent to water treatment. And electricity supply and usage was clearly the strongest contributor to most impact categories. Again, the dataset used is a strong contributor to the results. And in this case, the dataset used was for South Africa. And this pie chart shows that South Africa is heavily reliant on coal for energy generation. So options to reducing these impacts in the flow sheet are not necessarily attached to reducing energy demand in the flow sheet design, but energy supply. And to demonstrate this, a different electricity grid mix with more renewables incorporated in it was used, and a reduction in 10 of the impact categories is immediately identified. So just to summarize, the flow sheets that we proposed reduced sulfide, uranium, and arsenic in the tailings. So the solutions presented reduce environmental impacts that are associated with acid mine drainage, radionuclides, and arsenic, as well as producing gold as a value stream. Now, the thiosulfate flow sheet reduced environmental impacts more significantly than the cyanide flow sheet, and it was observed that the choice of lixiviant for extraction was the greatest determining factor, not only on technologies incorporated into the flow sheet, but on the contributions of these technologies to the ecosphere. The impacts of sections in the flow sheet included to extract greater value were overshadowed by the lixiviant choice. So it remains that economics may or may not justify their presence in the flow sheet. Finally, the LCA model and corresponding sensitivity analysis showed that South Africa's dependency on coal for electricity generation was a major contributor to environmental impacts for both flow sheets, and a transition to renewable energy can reduce environmental impact of mining operations. I just want to thank Kieran Cairncross, who did the work, the Royal Society and the African Academy of Sciences for funding and support. Thank you.